I want to start with a very small disclaimer. I'm not a probabilist at all, and almost everything I know from the probability theory I learned in last 10 years. Maybe it was too late. So what I'm going to tell you in these 3 lectures, it's about topological structure of zero lines or zero sets of random functions of several real variables. This is what I call nodal portraits. Questions about topological structure, people were interested in these questions, probabilists and electrical engineers, for many, many years. There were no, with one exception, there were no results about these things at all. And the reason is that the simplest topological characteristic is a number of connected components, that it's absolutely non-local characteristic. If you know what's happening in one place, you know what's happening in the other place. It gives you no idea whether zero line which you observe here and here belong to the same connected component or not. So you cannot apply local integral geometry, things like Katz-Rice formula or whatever. But in the last 15 years, there were 2 reasons why people from other areas started to be interested in these questions. And one of the reasons came from classical algebraic geometry, because there was a famous first part of Hilbert-Sixtin's problem, which asks about the number of connected components of algebraic curve of zero set of a polynomial of 2 variables in the simplest instance. Hilbert asked about the maximal number of components, but people started to be interested what's going on in average, and even how to formulate the question, how to pose the question. And the other motivation came from quantum chaos, came from Michael Berry, who is a physicist. There were many exciting and completely open questions about behavior of high energy eigenfunctions for Laplacian, say on surface, on Riemannian surface with negative curvature or whatever. And Michael Berry said something already in the 70s, which people call now Berry prediction, that if instead of looking at behavior of eigenfunctions with high eigenvalues, with large eigenvalue for individual eigenfunction, you may look at what's going on in random. And if you understand what's going on in random, then you will understand what's going on for individual eigenfunction, at least when the curvature is negative and constant. This is absolutely non-rigorous. There is no simple instance where Berry prediction is confirmed, where Berry prediction is disproved. So it's completely open. But for this reason, physicists and then mathematicians started to be interested from mathematical physics, started to be interested in what's going on with topology of zero set of Gaussian or random functions of several variables. And accordingly, there are 2 setups how to understand this question. So one setup, which is more related to Hilbert-Sixtin's problem, is what I call large degree model, or you may say large eigenfunction model. When you look at polynomials of large degree, they live on a sphere or on projective plane or on the torus, and you want to understand what's happening with the number of connected components of the zero set when this will be a random variable when the degree goes to infinity. The other model, which I call Euclidean model, so instead of taking large degree limit, you may look at stationary or translation invariant random functions of several variables. It lives in Euclidean space, and then we just take large box limit. We take large square or large cube or large ball. We compute the characteristic which we are interested in, we juxtapose it with the volume of this ball, and then we send the volume to infinity. People with some experience, they understand that these two models, though they look different, they are closely connected to each other. And Euclidean model is much simpler, just because you already have all difficulties, but it is much simpler because we get rid of any geometry in the Euclidean model. So you have this problem naked, and you may try to think about it. And so now about a few words about the plan of my lectures. So today I will start with some science fiction. It will be work done by physicists, by Bogomolny and Schmidt 10 years ago. And then I will speak about Euclidean model. And then tomorrow morning, I will speak about large degree model, and I call this Riemannian model because the proper setup is a function which live on some Riemannian manifold. And then tomorrow in the third lecture, I will speak about some fusion. When we will choose a model when our random functions are eigenfunctions of Laplacian. These are the simplest instance are spherical harmonics, and then you can prove much more than in the general setup. So this is the plan, and I start with science fiction. And before this, so all theorems, basically I'm going to present you three results after science fiction part will be over. All these three results are our joint results, which Fyodor Nazarov and I obtained something several years ago and something just recently. So let me start with Bogomolny and Schmidt. So they looked at Gaussian function in two-dimensional plane, which is stationary. This means that its distribution is translation invariant, and also which satisfies, which is an eigenfunction for Laplace equation. So the simplest thing to build this function. So if we have a this is our Gaussian guy. So we know the distribution is translation invariant, so everything is defined by the covariance. Covariance must be a function of the difference of the variables, and this is Hermitian positive function, so K. So K of U is a Fourier transform of some measure. The measure is called spectral measure. But let us choose the spectral measure. Let us choose now, for the purpose of that model, the spectral measure will be Lebesgue measure, which lives on a circle of radius 1 on the plane. Then clearly, this function f will satisfy Helmholtz equation. No, well, it depends. In my normalization, it will be 4 pi squared. Right, because Fourier transform, when you take Laplacian from this guy, you get obviously this equation. And they wanted to understand what's going on with zeros with a number of connected components in the large square or in the large disk. So they looked at large square. And first of all, it's very easy to compute the mean length of the zero line. And according to this computation, so they say, let's start with checkboard. Clearly, so let's suppose that this is a nodal portrait of our function. So here function is positive, here negative, positive, negative. The size of the cell is chosen in such a way that the length of the zero set will be according to the computation, which can be done rigorously using Katzer's form. Certainly, it cannot be the zero set of random function, because our function, with this nodal portrait, function and gradient vanish simultaneously at these points, and for random function, function and gradient cannot vanish simultaneously, almost surely. So then they said, let's do the following. Let's flip a coin independently at each vertex. And according to the coin, we will avoid intersections either on that or in this way, etc. And let's analyze what will happen afterwards. So we're interested in the number of components of the zero set. So how now you see the picture, which for many of you is very familiar. So let us first draw the lattice, dual lattice, say, through positive domains. And now what we did for each bond with probability, this is our dual lattice, for each bond with probability 1/2, the bond is either open or closed. So this bond is closed, so we need to erase this. This bond is closed, this bond is open. So what we arrived at bond percolation on quadratic, on the square lattice. So this was the first step in their work. They're physicists, they're not mathematicians. After that, using some cooking books which physicists have had already for many years, they opened this cookbook and they said that this bond percolation on square lattice should behave like Potts model, very similar to the things which Alice was telling in her lecture. And again, this reduction is not, as you may guess, is not rigorous at all. Mathematicians still cannot do anything with this model, but they predicted, they just computed a lot of things using this cooking book, and they made a lot of numerics, and their computations coincide well with the numerics they did. In particular, they predicted, say, that the mean number of connected components behaves like constant times r square. So it's proportional to the volume, the variance. They computed this constant. The variance also behave like some positive constant which they computed times r square. They found distribution of areas of these domains, etc., etc., etc. This is very, very beautiful, very, very challenging, but it's completely non-rigorous. Why it is non-rigorous? The reason is the very first step. So if you look at covariance function k of u many of you know that this is simply zero Bessel function. It's Fourier transform of Lebesgue measure on the unit circle. And for zero Bessel function, covariance goes to zero, goes to zero like 1 over square root of the distance. It oscillates, but it goes to zero very, very slow. So there is no any motivation, no any reason to suppose that, and this is a size of 1, of some constant explicitly computed. So there is no motivation, no reason to understand why what is happening on the size 1 is independent. Why we independently flipped coins at the each vertex. This part is very unmotivated even from physical point of view. And this is still a big challenge. So this was a big challenge to understand what Bogomolny and Schmidt did. So certainly there is no reason to believe that square percolation, bond percolation on square lattice completely describes what we see here. It's not true, but they physicists, what they said, one should read this like this, that there are some hidden universality why original question and that question belong to the same as physicists say universality class. And this is a real challenge, I think, for mathematicians to understand this, to try to explain this, and I hope that maybe some of young people who sit here will succeed in understanding this. But also to tell you up to which point we know nothing, so let me tell you about two questions which are very naive but related to this model, but which are completely open. So the first question is that almost surely there is no infinite nodal line or zero line. Nodal means zero because of people who are working with Laplace eigenfunctions. So if covariance would be positive, this is known. People, some probabilists, I think Ken Alexander and Molchanov did it, but they assumed that covariance is positive. Here covariance is oscillating and one cannot get anything from their proof because they used heavily Slepian inequalities. So this looks like a very, very naive and very, very simple question, and still there is no answer. And certainly this is true. And the other question, which is also absolutely open, is what's going on with if we move out of critical levels, that for each positive epsilon, probability that the zero set of f in say in the square in square of side R has a component of length bigger or equal than epsilon R, not zero set, sorry, the set where f is bigger than epsilon, I wanted. That this probability goes to zero when R goes to infinity. With this analogy with independent percolation, it is clear, this was done already, known already to Hammersley, that this probability, if we look at super level set with positive epsilon, that this probability should go to zero even exponentially with R. That we don't have large components for the set, but here it's absolutely unknown. And the obstacle is the same, a very slow decay of the correlation function. So these questions are, in my opinion, are very interesting, and one can start thinking about them. I'm sure this is true, I'm sure this is true, I have no idea how to prove this and that. And this is to show you that we're very far from understanding what's going on with zero sets or sub-level sets or super-level sets of this function. So more or less that's all what I wanted. With this I finish science fiction part. But nevertheless, it appears that mathematicians can prove something, and even sometimes it's more than physicists can predict. Also, I have to say maybe one more word, that the choice of square lattice is very much related to the equation which I erased. Why square lattice? So with square lattice, so imagine that we have minima at each cell, at each plus cell, maxima at each minus cell, and saddle point, before we started to perturb, but saddle points at the zero level. So zero is a critical value. If you look at this equation, clearly you see that at the places where function is positive, function may have Laplacian is negative, function may have only minima. At the places where function is negative, f may have only maxima. And so this is according to that. But also, as we learned in basic probability geometry or probability theory, there are Morse relations. So here they should hold asymptotically. So number of minima plus number of maxima should be equal to the number of saddle points. At least asymptotically up to some corrections. So this was the reason for choosing square lattice, not the other lattice. Because if you start with the other lattice, you lose this relation between number of minima plus number of maxima. So the model Bogomolny and Schmidt suggested was very much related to this simple elliptic equation. Okay, so now I start to speak about Euclidean model. So we have a stationary or sometimes I will say translation invariant Gaussian function. We have its covariance kernel. And K, as I explained already, is a Fourier transform of some measure which keeps all information. This is a spectral measure. And it contains all information, at least theoretically, about our process. And we denote by ZF the zero set, pre-image of the origin. So these are m-1 dimensional hypersurfaces. Almost surely they are smooth, no singular points. And we want to understand the random variable nRF, which is the number of connected components of Z of f in the ball of radius r. So when we need some agreement when we compute the number of connected components. So in my definition, I count only. So in this picture, if this is a ball of radius r, the number of connected components is 1. I count only connected components which are strictly inside the ball. But in reality, it doesn't matter so much. We need just to have some agreement what do we count. And now I can formulate the theorem. This will be our first theorem. Proved. So suppose that the spectral measure satisfies the following assumptions. I will call them ρ1, ρ2, ρ3. Measure has no atoms. ρ2 is not supported by a hyperplane. And ρ3, it has a moment of some order a little bit bigger than 4. So the last assumption, it will be clear in the course of the proof why do I need these assumptions. The last assumption is, simply says that our process is almost surely C2 smooth. Even a little bit more, C2 plus epsilon smooth. Then there exists a constant nu which depends on the measure and which is non-negative, so that limit when r goes to infinity n of rf over r to the m over the volume. Let me write over the volume of the ball of radius r. It doesn't matter, but this normalization I like more. Equals nu of rho, almost surely, and in mean. This is good, but it's not satisfactory because it says that there exists limit which is non-negative, but we want to be sure that it is positive. So, moreover, probably the most intricate things are lower bounds here. So, moreover, nu of rho is positive provided the following condition, which look strange, but I will explain it right now. That there exists a Hermitian positive compactly supported measure mu, so that support of mu is contained in the support of rho, and the zero set of the Fourier transform of mu hat is Fourier transform always, has at least one bounded. Well, what will I do now? I will write something here. Bounded connected component. So we give a condition, and I will try to explain you now that it is very mild condition, which tells when this constant nu of rho is positive. But this constant is absolutely secret. Our proof gives no idea how to compute this constant, and moreover, it gives no idea how to make tight bounds. So the best bounds which are known for this constant, the discrepancy is in 2 orders of magnitude, 100 times. The discrepancy between lower and upper bounds for this constant. But first of all, what does it mean Hermitian positive? Hermitian positive means that if you reflect the set at the origin, the measure will be conjugate. These measures are complex valued. It will be conjugate to the original measure. This is bounded Borel set. And this is more or less, this is equivalent as to say that Fourier transform is real valued. That the Fourier transform and cosine transform are the same, that sine disappears in the transform. So now let me explain you how to work with condition rho 4. So now I want to comment to condition rho 4. The first example, please.
Sorry, what does rho 2 mean? So what does it mean it's not supported by a hyperplane? I mean, it doesn't live on a hyperplane? No. There could be hyperplanes which have positive measure. What I said that support of rho is not contained in a hyperplane. Please. P is bigger than 2. So I need yes, I need some, it could be fractional number. I just need something to be sure that our process is C2 smooth.
So you have example when nu is bigger than 0. Do you have example when nu is 0?
In a sense, yes, but they are not so interesting. Yes, because, okay, I don't want, I may return to this, but in a more private setup. So let me explain condition rho 4. So sufficient, so suppose that support of rho contains a sphere centered at the origin. Like in Bogomolny and Schmidt model. Then we are done. Because simply take mu is a restriction of Lebesgue, is a Lebesgue measure on this sphere. It doesn't matter what is the radius of that sphere. Fourier transform of this guy is another Bessel function. And you even don't need to know anything about this Bessel function. Fourier transform is radial, and certainly it will have some 0. So in the 0 set of the Fourier transform, there will be another sphere. So immediately you get a bounded component. Another example. So this works in any dimension. Another simple example is in dimension 2. Suppose that another sufficient condition that support of rho cannot be covered by finitely many straight lines.
I will not elaborate why this is true, but this is also very simple. This is exercise in two-variable calculus to show that if support of the measure is not covered by finitely many straight lines, then you may find another measure. It will be a discrete measure. It will be a linear combination of 4 atoms for which zero set will have a bounded component. So though this condition looks pretty strange, what I wanted to say is that it's rather easy to check. These two sufficient conditions are, even the first sufficient condition is, for all examples I know, one can use this. All right, so now let me go to the proof. Well, the first step is something what I call integral geometry sandwich. For n of Rf. Still, though I try to convince you that integral geometry doesn't work, you can get something using integral geometry. I will need some notation. So if I have a ball centered at the point x and of radius r, then I denote by n x r f. Okay, I will not write f. Everything is. So usually I will skip f. This is the number of components in this ball, which are strictly inside the ball, and n star of x r f is the number of components that intersect the closed ball. So in this picture, n star equals 2. Though from the point of view of the ball, these are two different components, but I count them as one component. So then we have the following bound. N of R, this is the quantity we are interested in, bigger or equal than integral over the ball of radius. So I have parameter R, which is less than R capital. Integration over the volume with respect to x. So this is what I call integral geometric sandwich, and it's again very simple exercise. So let me show, for instance, the lower bound. This is just Fubini formula and definitions. So to compute, roughly speaking, if we have a large ball and we want to compute how many components we have, so instead of computing components on the large ball, we can compute in small ball, then integrate over position of the center. We cannot get identity, but certainly we will get lower bound in that way and upper bound in this way. This is just Fubini, and probably I will skip it. Now
Another remark is, so let me elaborate a little bit the sandwich, that this guy is not so easy to work with, but again, from calculus, we know that if we have such a component, that somewhere here, there should be at least one critical point of restriction of our function to the sphere. So instead of, so I may estimate n star by n of xr plus nc of xr, where nc is a number of critical points of the restriction of f to the boundary of our ball. This is just an obvious bound. Zeros of gradient.
Oh, okay.
Yes.
Okay, so it's
Yes. Yes, where the gradient vanishes. So I restrict our function, so in two-dimensional picture, I restrict my function to the sphere. I get a function of one variable parameterized by the circle. This is a circle, so it vanishes at these 2 points. And as you learned when you were an undergraduate student, there is a point where derivative vanishes, right? All right, so this was the first part. So this was the sandwich I want to work with. This is the lower bound and this is the upper bound. Now the second idea. Let me just rewrite the sandwich. Let me recall that distribution of our function was stationary, was translation invariant. So let me introduce the shift. Okay, I will write it with a purpose. I will write it a little bit down. Is it okay if I'm writing here? This is a shift acting on our functions. So now we can rewrite these two guys in the following way. So instead of n of xr, I may write n of r, but applied to the shifted function, n of small r. And here, this will be again n of small r applied to the shifted function. And then this is this guy of small r applied to the shifted function. Because distribution of our function is translation invariant. So the next step speaks for itself. You can easily guess what will be the next step in the proof. So we are interested, let us see what do I want to prove. I want to study n capital of a volume. So let me divide this by volume of B of R. So then I need to divide this by volume of B of R. And I need to divide this by volume of B of R. So what does it remind you? It reminds ergodic theorem. So our stationary process is Gaussian. There is a famous theorem proved more or less simultaneously by Fomin, Maruyama, and Grenander, which says, and this explains why we need this condition, which says that if a spectral measure of Gaussian process has no atoms, then this yields ergodicity. Which means that shift acts ergodically on right probability space. There are many choices. We can deal with C2 functions on Rm with Borel sigma algebra generated by Gaussian measure and take Lebesgue completion. Once I had, after I started to do things related to probability, I got a report on some paper referee report on a paper we wrote with my colleague Boris Cyrilson, and the referee said that, usually people in probability, they don't explain why everything is measurable. But, okay, we respect your decision to explain this. So anyway, for this reason, since most of the audience came from probability, I will not explain why everything is measurable. But Famingren under Maruyama theorem says the distribution of this guy is measurable, and then you need to prove that this functional on functions is measurable with respect to that sigma algebra. So if this guy is ergodic, this guy is ergodic as well. Anyway, if we apply multidimensional ergodic theorem, this is a classical theorem due to Wiener, we obtain, now I need to erase something. I want to keep conditions on C with Blackboard. So now the next step is ergodic theorem. Wiener in this case, which says that for each, so we keep rho, we keep R small is fixed, R capital tends to infinity, and we know that expectation of this guy over the volume is less or equal than the lower limit when R goes to infinity for our quantity is less or equal than the upper limit when R goes to infinity of this quantity. And this is less or equal than sum of expectations of this guy plus this guy over volume B of R. This holds almost surely. Also this holds in mean. So I apply ergodic theorem to the left and to the right hand sides of our sandwich. And let me emphasize that we get it for any R, for any small r, which we used in this sandwich. Now, this thing, we need to get rid of number of critical points. And this is simple. The next step, this is absolutely classical device in Gaussian processes. It is called Katz-Rice premise. When you deal with critical points, you can actually compute them. I will not tell you, I believe many of you know how to compute. You can write a formula for the number of critical points. And using this formula, look, this guy, these are critical points of restriction of our functions onto m-1 dimensional sphere. So it scales like volume to the power r-1. And in the denominator, we have volume of the ball in Rm. So this guy scales like r to the power m. So if we send now r small to infinity, this guy will go to 0. Just because mean number of critical points bounded by constant times r to the power m-1. Here are people in the audience who know these things much better than I. Well, so what remains now? So we proved that this secret constant exists. We have no idea how to compute it, because this was just our mean. And what remains is to show that that if you have this condition, the secret constant is positive. This I will do in remaining 10 minutes. Maybe I will try. I want to try to keep everything on the blackboard. So the last part is condition rho 4 yields positivity. So let's think, what do we need to prove? What we know about, what is our constant nu? We know that nu of rho is just from the proof. Look at this inequality. Nu is a limit for this guy. So nu of rho is bigger or equal than mean number of components, which anyway we know nothing about it. And this holds for any r. So if we can find, if we know that there exists just one value of r such that, so this still with question mark, such that zero set probability that the number of components in the disk of radius r small is positive, if we know that we have at least one component in some ball, then this expectation automatically will be positive. And we immediately will get that our secret constant is positive, without knowing nothing about its value. So this is what we need to prove. If we have at least one component, then the proof shows that we have very many of them, like the volume. Now I need to erase something. Okay, sandwich is written on the blackboard, so I can erase this. And for this I want to use another pretty standard Gaussian lemma. So our original argument was quite complicated and used some hard analysis, and it was very good to have friends in your department who know well probability theory, and in my case I have a friend who suggested to use the following lemma, that for any positive epsilon, so suppose that mu is as above, as in our condition rho 4. So this is Hermitian positive measure with support in the measure of rho. Then for any positive epsilon, probability, and for any ball B, probability that our process is close, epsilon close to the Fourier transform of my measure in C2 norm, for us C norm will be enough, is positive. That whatever measure we get just with this property, there will be balls where our stationary function will be very close to Fourier transform of this measure. If you don't believe into this lemma, ask me a question after I will finish the proof. I will explain. But now let me assume that this is true. This is just simple Gaussian stuff. And if this is true, then we take mu with zero set such that mu as in rho 4, take ball B such that it contains a component of the zero set of the Fourier transform. Measure was compactly supported, so Fourier transform is a real analytic function, and zero sets, all components are isolated. So if we had components of the zero set of mu hat, and if our function was even uniformly close in the closed ball, then we get that the probability that n of R0 F is positive, right? As we teach students, because if this was our ball, this was component of the zero set of mu hat, component is isolated, so if our function is uniformly small to mu hat, it must have zero component somewhere nearby. Maybe this way, maybe that way. That's it. So this is the proof of theorem 1. And this proof leaves many questions open. We don't know what's happening. So I will, maybe in the end, I will list 2 or 3 questions which I would love to have the answers. Okay, I will not. One question is what's happening with the variance. One can get some upper bound for the variance, but I believe that the variance also grows like the volume, but we cannot even show that the variance goes to infinity. The other question, which is very, very intriguing, is so it's clear from the proof that most of components are of unit size. What's happening with large components? So let's fix some parameter alpha between 0 and 1, for instance, 1/2. And let's look at components with diameter comparable with r to the power alpha. Our proof doesn't work at all, so we cannot say anything what's happening with large components. And certainly the most intriguing question is to understand some nature of the secret constant nu of rho. Our proof is that it's clear that you cannot extract anything from it. You can get some upper bounds by number of critical points. These upper bounds will be very, very far from the realistic one, but from which, how it depends on rho, start to perturb rho a little bit, what will happen with this constant. So everything is absolutely open, and I do not have any idea about the nature of this constant nu of rho. Thank you very much.
Concerning your condition rho 4, you want to show that this probability is positive.
Yes.
Why it's not possible to consider a restriction of the Gaussian field to a one-dimensional line, and then using Katz-Rice formula show that there is at least 1 0. Then
No, but you need to know, look, Dmitry, you need to know that the picture will not be, it's on the opposite. You need to know that Gaussian function, because it can be like this. I want to compute components which are inside. So if I know that restriction on the circle has zeros, it doesn't tell me, because more or less now the answer to your question, so it's not written, but it looks like we have an alternative. If condition rho 4 or something like rho 4 does not happen, does not occur, then with almost surely there are no bounded components at all. So we have an alternative. Either we have many bounded components, or almost surely we will not have them at all, because it's more or less clear from the proof that if you find one bounded component, then you will find many. So if you have measures which do not satisfy this, some peculiar measures, then I believe that almost surely all components will be unbounded. But for the most interesting examples, measures are not like that, that's why. But I think this is what should happen. Did I answer to you? Yeah, no. Lemma? No, well, I can explain. No, lemma is pretty well. Look, how one may think about Gaussian process. One way is to start with covariance. Another way is to start with spectral measure. So if you have a spectral measure rho, If we started with spectral measure ρ, then we can build the space of functions which are symmetric, which are in L2 of ρ, and which are symmetric with respect to the origin. Then, if you take Fourier transform of that space, you will get something what is called reproducing kernel Hilbert space. And then our process, then you choose any orthonormal basis in this space. And then you simply have another representation for your process. Your process equals sum of psi n En of x, where psi n are standard Gaussian. This series will not be in the space, but the series will converge almost surely in C2 on Rm. This means on any compact subset. And from this representation, first one can see that if you had a function from this space instead of mu hat, then this is true. Just you take finitely many terms, and this will be function from that space. This space probably is called Cameron-Martin space or space of admissible shifts. And then you need to show that we want Fourier transform of measures, and here a Fourier transform of L2 functions, but this is again a very simple approximation because weak convergence of measures, because everything is real analytic, yields uniform convergence of Fourier transform with all derivatives on compact set surds. So this is the idea behind this proof.
Perhaps the existence of this limit is just a consequence of subadditive Ragone theorems.
Yes. But this is what I said.
And this function is
No, I didn't.
imperative.
No, I just said which function?
The number of connected components inside the set. It is a super additive function of the set.
Oh, super additive. So if you have two.
Union of two sets?
This I'm not sure because the way I count. Because look, if you unite two sets, it could be. Okay, this is more or less what I said because our proof is we use just ergodic theorem. But there could be pictures like this, and if you count, you need some accuracy, because if you have a component which comes this way, you need an agreement.
The components that are strictly inside, yeah?
Yes, I didn't claim that this is something complicated. On the contrary, my claim is that everything is very simple.
It would help or not if in your rotary you will have something very simple. Just you will have a compact subset, so all the relations are integral functions.
No, because in the Bogomolny-Schmidt model, this is just Lebesgue measure on the circle.
Something very smooth.
No. To get, as I said, the most tricky part for us was lower bound. Originally, in our first paper, we get it in a very complicated way, constructing by hand some bumps. And no, I don't think that I don't see how any information about spectral measure helps.
So your relation will be integral function.
Yes.
It will not help you.
No. I don't see. They are Pelley-Wiener class. I don't know. Yes, they have entire functions, but we count something on the real. At least I have no idea. I thought about this looks very strange, but because we count something related to real topology, to real valued topology, analytic continuation doesn't help, because when you continue into C2 onto CM, anyway everything will be connected. So they connect somewhere after analytic continuation. And